I know a lot of people have recently been quite confused about power sets and that 2 to the x set and function spaces, and some of you have gone so far as to ask me to record a video on this. Now, I feel I have quite a good understanding of this topic, but I'm not an expert, I don't know everything, so anything you hear in this may be wrong, but hopefully it may improve your understanding a bit, and hopefully it's all correct. So to get started, we're going to talk about function spaces. Function spaces basically are things that contain functions. A function space between two sets contains all the possible functions from the first set to the second. So an example of this would be the function space between a set containing two elements and a second set containing two elements. So if I draw an example of this, we have two elements in one set and two elements in a second set. And one way of mapping the two would be like this. Another way of mapping them would be like this. And then there are two more ways where both of them map to one element, like so, as well as like so. And those are all the possible mappings of the two function set to the two function sets. So all those mappings put together form the function space, and indeed it contains just four functions. Now the important thing to remember is a function space is literally just a way of saying the list of all possible functions in this scenario. So our scenario was mapping between a two-element set and another two-element set. The function space is just all the possible functions in this scenario. It's not special in any way, it's just a list of a whole bunch of functions. Now, another thing that you need to understand is the y to the x notation. So suppose we have a set x with little x elements and a set y with little y elements in it. The function space from x to y contains exactly little y to the little x functions. And that's because for every element in our first set, it can map to any one element in the second set. So an example of this, if our first set is a singleton containing one element, and our second set contains 7 elements, then there are 7 different functions. Now I'm going to draw a 3-element set here, but you get the idea. There's one function that does this, there's one function that does this, and one function that does this. And obviously there's just those 3 because you're only mapping from one element. Now this does still fit with this notation because 3 to the power 1, or in this case it would be 7 to the power 1, is still 7. There are 7 different functions in the function space. And now if our first set has, say, 2 elements and the second has 5, so we have 2 elements and 5 elements, then there's 5 ways of mapping the first element and 5 ways of mapping the second. So the first element, for example, could go here. And the second element could, for example, go here. Now there's exactly 5 ways of mapping the first element. It can go to any one of the second elements. And there's exactly 5 ways of mapping the second. And they're completely independent from each other. Now, a function is a combination of these two mappings. So what I just drew would be a function. This would be a function as well. So where they both map to the same element, that would be a function. Where they both map to different elements, all of these are functions. And the mapping of the first one, of which there are 5 ways of doing it, and the mapping of the second one are independent, so there's 5 times 5, or 5 squared, total functions. And you'll notice this fits with the notation. We're mapping from the 2-element set to the 5-element set, and indeed 5 to the power 2 is the number of total functions. And that's where this notation comes from. Set theorists have basically decided that if I'm mapping from set x to set y, I know that I'm going to have y to the x functions, so I'm just going to write the mapping from set x to set y as y to the x, and that's where that 2 to the x set comes from, which we'll look at in a moment. Now we're going to take a look at the power set. Now the power set is basically a set containing all the possible subsets of a set. So if the cardinality of your original set is little x, the cardinality of your power set is going to be 2 to the little x. Why is this? It's because we make a subset by either including or excluding elements from the original set. So each element can either be in the subset or out of the subset. It has two choices. If my set, for instance, has one element, which I will demonstrate like so, just one element, there are two possible subsets. So there's two possible subsets because my one element can either be included or not included, and that's it. So you have two possible subsets. And indeed, if I have three elements, each element also has two choices, and again it chooses independently, so there are 2 times 2 times 2 different subsets, which means there are 2 to the power 3 different subsets. So here's an example of power sets. Let's take a set with 3 elements, A, B, C. And the first element can be in the subset or not, so there's 2 possibilities, and therefore the possibilities in total double with each element. What do I mean? Well, let's actually make the power set of A, B, and C. So here I have that first choice. So A can either be in the power set, which is what happens up here, or it can be not in the power set. Now B and C we don't know, so I've left them as question marks. In both these cases we don't know whether B and C are in the power set. So now we move on one step down. Now B chooses. Now you can see the number of options doubles. So on the left hand side here we have one option where B chooses to be in the power set and one option where it doesn't, or rather in the subset, sorry. And here we have, again, one option where B chooses to be in the subset and one where it doesn't. And again, for the options of C, again, the options double. So now we have 8 total options, and these contain the entire power set, essentially. So the power set is all the possible subsets, and here they are. So this whole thing is the power set. And you can see we've made it by just looking at all the possible options. So A either chooses to be in the set or not in the set. Then B either chooses to be in the set or not in the set. And then finally C chooses to either be in the set or not in the set. So here's an example of where they all chose to be in the subset. Here's an example where they all chose to not be in the subset. And you can have anything in between. Here A chose not to be in the subset, B chose to be in the subset, and C chose to be in the subset. So that's just how we make a power set. We consider all the possible combinations of subsets by basically letting each element of the set choose whether or not to be in the subset. And all those possible subsets together are just the power set. So then we have the 2 to the x set. This set contains all the possible functions from a set x to a set with 2 elements. So this is that y to the x notation. Let's say x is our 3-element set again. And our set with 2 elements is 0 and 1. This can be any set with 2 elements, but it's convention to just use 0 and 1. So each element from set x has a choice of 0 or 1. It has 2 choices. And the 2 choices are independent, so they lead to 2 times 2 times 2. It's 2 to the power 3 different mappings. So here's an example mapping. A maps to 1, B maps to 1, and C maps to 0. Now any combination of these can be a mapping, and altogether they make that 2 to the x set. Now you'll notice the mapping is denoted with the squiggly brackets because it itself is a set, and then it has pairs, so what maps to what. So A will always map to 1 or 0, B will always map to 1 or 0, and so will C. And the power set of A, B, C was made by giving A, B, and C 2 choices, and so was this set. So you can see they may be in some way related. So how do we find a bijection between these two sets, the power set and the 2 to the x set? Well, let's say x is a set of A, B, C, and D. We've made it slightly bigger. This doesn't really affect much. The power set has all its possible subsets, while the 2 to the x set has all its possible mappings to 0 and 1, or any other 2-element set. So an example mapping from this 2 to the x set, So this is just one element from the 2 to the x set which contains all of these mappings. Here's an example mapping. A maps to 0, B maps to 1, C maps to 1, and D maps to 0. How do we turn that into a subset? Because that's what we want to do. That's what a bijection means. It means we can relate each one of these to exactly one subset, and we can relate each subset to exactly one of these. So the way we do that is each of these elements makes exactly one of two choices, 0 or 1. Let's say 0 means it's not in the subset and 1 means it is in the subset. Well, our subset becomes BC. Why? Well, A maps to 0, so it's not included in the subset. B maps to 1, so it is included in the subset. C maps to 1, so it's also included in the subset. D maps to 0, so that's not included in the subset. And therefore we get a subset of just B and C. So you see we can relate a mapping like this to a subset. Now can we do it the other way around? Yes, let's take a subset, A, C, D. It's just an arbitrary subset which is part of the power set, and turn it into a mapping which is part of the 2 to the x set. Here's the mapping. Now where do we get this from? Well, A, you can see, is in the subset, so it maps to 1. C, or rather B, is not in the subset, so it maps to 0. C is in the subset, maps to 1. D is in the subset, maps to 1. Everything that's in the subset will map to 1, and everything else just maps to 0. And that's how we relate subsets to mappings. And you can see we can relate each mapping to exactly one subset, and each subset to exactly one mapping. So therefore, we've got this bijection, and a mapping of all zeros would be the empty set, by the way. So if A maps to 0, B maps to 0, C maps to 0, and D maps to 0, what that really means is that none of them are included in the subset. So we just get the empty set as our subset. And of course the empty set is a subset of the power set anyway, so it's fine. So this mapping that we just showed is injective and surjective, so it's a bijection. Now the reason for that is essentially it's 1-to-1 in both directions. There is exactly one mapping from X to the 2 element set for each subset. You can take any mapping and turn it into a subset, and any subset and turn it into a mapping, and those are 1-to-1 relationships in both directions, and therefore it's a bijection. So essentially that's how you get that bijection between the power set and the 2 to the x set. So hopefully that helps. If there's any questions or comments, then message me, leave them as a comment, and if there's any problems with this, if I've gotten anything wrong, then please let me know as soon as possible, and hopefully this helped.